Speaker, as he says, Brian Gullett is a scientific and technical professional, senior research engineer with the Environmental Protection Agency's Office of Research and Development, which is located in Research Triangle Park, North Carolina. He has served as the acting division director for the Air and Energy Management Division, as an Embassy Science Fellow with the Department of State in Stockholm, Sweden, and has been a visiting scientist for 1 year with U.S. Navy's Naval Surface Warfare Center in Annapolis, Maryland.
Thank you very much, Monica. I appreciate it. My talk, obviously, sampling of in situ burn emissions using a helium-filled balloon, and note the disclaimer down at the bottom of the graph. So in 2010, during the Deepwater Horizon disaster, little was known about the emissions that come off of oil burns at sea. And obviously, this is a way of trying to eliminate some of the problems of oil in terms of washing up on shore, et cetera. But the EPA's Office of Research and Development then commissioned a study to try to find out whether this burning practice actually produced chlorinated dioxins and furans. Of course, these are fairly toxic compounds, and they're formed primarily from incomplete combustion of fuels in the presence of surfaces that act as catalysts, and obviously a chlorine source. So in this case, obviously the surfaces are the particles themselves, and the chlorine source is obviously the chlorine in the sea. So just a quick review of in situ oil burning in case you're not familiar. Basically, the Coast Guard oversaw a number of operations in the Gulf in which multiple fleets were sent out of paired trawlers, as you can see in the left-hand graph, and they towed behind themselves a boom which collected the oil, and when it was thick enough, they dispatched a work crew boat. See one here where it actually has a net on top of it. That's where they had a marine biologist looking for turtles that were stranded in the oil. And then they would actually ignite the oil when it was thick enough with gelled kerosene. As the schematic in the bottom shows, we were trying to sample the emissions from the plume of the burning oil with an aerostat, a tethered aerostat or a balloon. It's filled with helium and was affixed to the back end, the stern of a 220-foot workboat. So these are some pictures from our sampling effort in the Gulf during the oil collection and the disaster. We used, as I said, a helium-filled aerostat. We built a custom sampler, which you see in the bottom right-hand side. This is what we actually termed the Flyer. That was the version that was in 2010. It's undergone many different changes since then. Our burns and our sampling was aptly overseen by Master Chief Yeager. As you can see on the left, we filled the helium-filled aerostat on the fantail and stern of the workboat and attached it to a winch and did our best to project it into the plumes of the burning oil. So I'm attempting to show a video here. It's a little bit choppy, but I took this video. This just gives you an idea what it looked like when we were out there sampling. It's as you can imagine, it's very hard to maneuver a 220-foot ship with a tethered balloon into the smoke plume, especially when you are not allowed to throw any wake to disturb the oil that's corralled within the booms. And sometimes the wind direction and the direction of the two trawlers do not agree. This gives you an idea of what it was like when we were out there for 4 days. The Flyer, or the emission sampler, is attached to the bottom of the aerostat. And this is a pretty typical scenario that you can see here. So we're actually controlling these sampling pumps from the ground using a telemetry system. And obviously when the balloon is not in the plume, we are not sampling because we don't want to dilute our sample with background air. Pretty typical scenario there. So what were our results? We had 215 minutes of effective sampling over 27 burns in 4 days. The dioxins were detected, although they were at pretty low levels equivalent that you might find when you're actually burning just typical biomass. The PM was actually pretty high. The particulate matter was pretty high. So we calculated approximately 7% of the actual oil that was burned was released as particulate matter in terms of the mass. The PAHs, the polycyclic aromatic hydrocarbons, were also fairly high, predictably high. We did a follow-up study later on where we analyzed just the particles that were actually captured in the sail of the balloon. The sail is the thing on the bottom of the balloon that keeps it faced in a certain direction. And we found dioxins on the particles, but not as much as in the gas plus the particle phase, which we sampled earlier. These conclusions are actually at odds with previously published research which suggested there were no dioxins formed during the Newfoundland burn experiment, which we have refuted. Obviously, the particles, as predicted, are primarily carbon, and we did test for mutagenicity, and the particles were fairly mutagenicity, much more less so than diesel exhaust. So we've actually done some tests since then as part of the natural resource damage assessment. We've extended the original flyer, which you saw on the bottom right of a previous slide, into what you see here. This is actually two sampling apparatus that we call flyers, and they're side by side. And instead of obviously lifting them from a helium-filled balloon, in this case we had a relatively small fire, which was done at the Army's Aberdeen Test Center, and we suspended the sampling platform into the plume by means of a crane, which was moved around to find the optimal location of the plume. We had a number of different instruments, obviously more so in this case since we had some land-based instruments. We also did an analysis of the residuals by collecting the oil to see how much residual oil was found. And barring any unforeseen technical difficulties, this is another video, which you'll see here, of the oil burns. Two different views of the burns from about a 1 meter squared pan of Gulf Sweet crude that was miraculously obtained from the oil repository. And this is burning at Aberdeen Test Center in Maryland. So we're sampling the emissions here, and we are quantifying the residual oil that's left over. So what did we find in this work that we did a few years ago? We actually found an awful lot of residuals. 29% of the oil was retained as an unburned oil mass. This was actually much higher than we had found in the literature. I don't know whether this was a scale effect because it was a relatively small fire or not, but anyway, the literature reported much, much lower values. This is a little bit disconcerting if this holds out on a larger scale because it means that a lot of the oil that's burned is not burned and it becomes a sinking kind of residual. The particulate matter was, again, pretty high, similar to what we found in the Gulf. The particles were extremely small. They're 221 nanometers in mass median diameter. This is an extremely respirable size. It was bimodal in distribution. Again, 2 micrometer or 2,000 nanometer particles. Combustion efficiency was high if you're only looking at the gases, but if you also include the fairly high particulate matter, then it becomes a pretty relatively poor combustion. We did an excellent job at doing a mass balance on the emissions, which is pretty surprising. More recently, we've started to do some work with BSEE, the Bureau of Safety and Environmental Enforcement. This is work that we're doing with the Corps of Engineers up in Hanover, New Hampshire. We're taking basically that same platform that we deployed in the Aberdeen Test Center to work a couple of years ago. Again, we're putting over oil burns with a crane that's moving around, and the operator's doing a heck of a job moving the samplers into the plume. And what we're doing here is to support work that BSEE is trying to do and to improve combustion efficiency of these in situ burns. There's a couple different technologies that they're employing to promote the burns to get better combustion efficiency, and so this is what we're actually measuring that for them. This is work that's ongoing. We've had one trial up there, and we'll have a second trial coming up in November. So there are limits on the current method. I hinted at it, obviously, when you're trying to maneuver a helium-filled aerostat that's tethered to the back of a ship in the Gulf. There's some limitations on that. We've also applied this method with the newer aerostat you see right here and a larger sampler. We've applied this method also to forest fires, to measuring emissions from forest fires. We've also done a lot of work with the Department of Defense as they try to get rid of obsolete munitions. They'll burn propellants, they'll blow up bombs, and these plumes have to be measured for their emissions, and we've actually been successful at positioning this into those plumes also. But these limitations are obviously safety issues. The equipment can be hit by shrapnel, etc. Trees are always a problem when you're trying to sample. It also takes a lot of people and a lot of helium. It takes over $2,000 worth of helium to fill up one of those balloons. You do have to top them off, as the earlier speaker said. If you get a hole in them, you lose helium. That's a problem too. So you also have to predict where the wind's going, and that can be a difficult one. So more recently, we have applied unmanned aerial systems, or drones. These are drones that have been commissioned by other people and have been owned and flown by other people. So for instance, recently we teamed up with NASA Ames. They brought their hexacopter drone, and we affixed a new sampling system. The flyer that you saw before weighs up to 55 pounds. At least the modern version does. We have taken advantage of modern GPS, small sensor, 3D printing, miniaturized electronics to produce what we now call the colibri, which is a smaller sampler. It's about the size of a shoebox. Colibri in many languages means hummingbird, and the obviously embodiment of this was to put it on a hummingbird of sorts. So this system measures an incredible array of pollutants, maybe not all at once, but it all depends on what the source is. But these are a list of some of the pollutants that it will measure. And this is sort of a cutaway, an opening up of the colibri so you can see some of the internals. There's a carbon monoxide and a CO2 sensor. We can collect particulate matter by mass or even by particle size versus time. We can analyze for metals and ions. We can look at energetics, semi-volatile organic carbons, volatile organic carbons. We have a black carbon sensor that's either batch or real time. We can look at brown carbon and other pollutants also. And this weighs about 3.5 to 4.5 kilograms, and obviously it has to go on a fairly heavy lift unmanned aerial system. As you see here, this is a model that actually was shown by an earlier speaker. But this system gives us a much more degrees of freedom in terms of being able to get into plumes. You can obviously operate them off of ships. It's not a problem. Again, we have applied this again to open burning, open detonation of military ordnance, to forest fires, etc. So this is a real great new advance that you'll see much more of in the future. And I actually believe that, as far as I can tell, we have probably the most advanced emission sampling system on any UAS that I've ever seen so far. This is actually a Google Earth flight path, a three-dimensional path of one of the flights that we did for an open burning of propellant at an Army site in Virginia. If you follow the numbers, we took off from the source, which was an open burning pan of actually rocket motors that were obsolete or off spec. And then you follow the numbers through. That's actually the flight of the unmanned aerial system. The colors indicate the carbon dioxide concentration. Obviously, as it gets toward red, that's higher. The reason why we follow carbon dioxide and actually have it telemetry down to the ground is because sometimes it's hard to tell whether you're actually in the plume or not. So if we can see this CO2 concentration instantaneously, and we know that it's extremely above ambient levels of, say, 400 ppm, we know we're in the plume and we're effectively sampling. So that's sort of a typical flight path. in summary, we've employed an aerial sampling method at the Deepwater Horizon. We've advanced that considerably in the last 8 years. We've applied it on forest fire emissions and other sources. For the oil burns themselves, the PM was extremely high. It was about 8% of the mass that was burned. The residuals, at least in our experiment, seem to be extremely high, of some concern. And the emissions are also mutagenic, which is reasonably predictable. We are working towards higher combustion efficiencies and working with Bessie to try to improve this technique of in-situ burning. A number of references that are available. If you just ask, I'll be glad to send them to you in PDF form. These are a couple more photographs that are kind of small, but they're ones I took out in the Gulf. I want to thank my co-performers. There's a whole slew of them, so I won't go through them, but a lot of different agencies and my colleagues. Again, thank you very much.